Determining the percent that each element makes up in a particular chemical compound can allow us to determine the chemical formulas of compounds. Now, before we talk about the chemistry of this, let's do a little bit of reviewing about percentages, since I imagine some of you have not used these for a while. So, to calculate the percentage of an item, you need to know two things: the part and the whole. The part is whatever portion of the total you're interested in, and the whole is everything. So, for example, suppose I wanted to determine the percentage of male students in my class. I would need to know two things. I would need to know the part, which is how many male students I have, and the whole, which are all the students together. I would simply divide those two, multiply by 100, and that would give me the percentage of male students in the class. So let's take a look at an everyday example here. Let's suppose that I wanted to determine the percentage of pennies in my change. First, I would have to know how many of each kind of coin I had in my change. So let's suppose we had 7 pennies, 3 nickels, 3 dimes, and 1 quarter. If I want to determine the percentage of pennies, the pennies would be my part, all the coins would be the whole, and I would simply divide the two and multiply by 100 to get my percentage. Turns out, though, there's more than one way to do this. We could do it by number. We could count the pennies, and there are 7. We could count all the coins, and there's 14. And based on that, we get 50% pennies. So based on the number, pennies is the greatest or largest component of my change. On the other hand, we could also do it by value. We could measure the value, so 7 pennies is worth 7 cents. All the coins are worth 77 cents. Now we come up with 9.1%. And so based on the value of the coins, the pennies is the smallest component of my change. So, which one of those is correct? And the answer is they both are. They're just simply two different ways of determining percentages. So whenever you tell someone about a percentage, you always need to specify what you're basing that percentage on. We could have determined the pennies percentage based on the mass. We could have weighed the pennies and weighed all the coins. We could have based it on volume. There's lots of different ways you could do it. So as we'll discuss in a couple of minutes, when we do percentages in chemistry, we're always going to do it the same way, and we'll specify what that is on a couple of slides from now. All right, let's try calculating the percentages of elements in an actual compound. So let's take glucose, C6H12O6, and figure out the percentages of carbon, hydrogen, and oxygen in that compound. Now, as we mentioned before, there are two ways that we could approach this. We could base it on the number of atoms in the molecule. So for carbon, we have 6 carbon atoms out of a total of 24 atoms, so 6 divided by 24 gives us 25% carbon. We can calculate the hydrogen. There are 12 atoms of hydrogen out of 24, so that's 50% hydrogen. And the oxygen, there are 6 out of 24, which makes it 25% oxygen. So based on the number of atoms or moles, the compound is mostly hydrogen. Now the other way, of course, is we could base it on mass. We could weigh the various elements in there. So for carbon, we have 6 moles of carbon times 12 grams per mole. That's 72 grams. If we add the 12 moles of hydrogen and the 6 moles of oxygen, we get a molar mass of 180, and that gives us 40% carbon. Same thing with hydrogen. 12 grams of hydrogen out of 180 is 6.7%. And for oxygen, 6 moles at 16 grams per mole is 96 grams of oxygen, so it's 53.3%. So based on the mass of the elements, oxygen is the most abundant, and hydrogen is actually the least abundant. So which one are we going to use? Well, back in the early days of chemistry, back before people even knew what atoms were, and they had no chemical formulas, the only way they could go about identifying compounds was by mass. They would take a sample of a compound that was unknown, weigh out a sample of it, maybe 10 grams of some substance. They would then chemically treat it, and they would separate the elements individually. So they would split up the compound into carbon, hydrogen, and oxygen. They would weigh the carbon, weigh the hydrogen, weigh the oxygen, divide each of those by whatever size sample they started with, and they would get percentages. And that was a really good way to identify a chemical compound. So in the future, we are always going to do this based on the mass percentage, not the number percentage. So how do we go about using percentages to identify compounds and determine their chemical formulas? Let's take a look at an example. Let's suppose that a scientist has prepared a new compound in laboratory. They analyze the compound by separating the elements and weighing them individually, and then dividing the mass of each element by the total sample they started with to come up with percentages. And they came up in this case with 40% carbon, 6.7% hydrogen, and 53.3% oxygen. You probably recognize that these are the same percentages we found for glucose just a couple of minutes ago. So can we conclude that the scientist has indeed produced glucose? Well, it does seem to match up nicely. The percentages are precisely what we would expect for glucose. However, ribose, C5H10O5, has those exact same percentages. Lactic acid, C3H6O3, same story. Acetic acid, C2H4O2. All four of these compounds have exactly the same percentages of the elements. So what do all four of these have in common? Well, if you take the formula for glucose, you'll notice that all three of these subscripts are divisible by 6. So we could simplify this formula by dividing by 6 and getting CH2O. That tells us that the ratio of the elements in the formula is 1 carbon to 2 hydrogens to 1 oxygen. The same thing is true with the other three. We have 5, 10, and 5, which divided by 5 gives us 1, 2, and 1. Divide the lactic acid by 3 or the acetic acid by 2, they all reduce down to CH2O. So CH2O is the empirical formula. We talked about empirical formulas in an earlier video. So all of these compounds have the same empirical formula. So we can't be sure which of these it is. It could be a myriad of other compounds. It could be C20H40O20 for all we know. There's an almost limitless number of compounds that could have a ratio of 1 to 2 to 1. So we're going to need additional information to figure out which of these compounds happens to be our mysterious compound that the scientist has just prepared. So how do we get from the molecular formula, or get the molecular formula from the empirical formula? The molecular formula, that's the true formula, the actual molecule. The empirical formula is simply the ratio of the elements, so that's not the same thing. It's useful information, but it's not everything that we need. So let's suppose we go back to our original question here. We have a new compound that's been discovered that has those same 3 percentages we've been talking about. How do we determine the actual or molecular formula of the compound? We need another piece of information, and that piece of information we need is the molar mass. It's sort of like an algebra when you've got 2 equations and 2 unknowns. You can't solve for 2 unknowns unless you have 2 equations. So our 2 equations are the percentages and the molar mass. So we know the empirical formula is CH2O, and let's suppose that we determine that the molar mass of the mysterious new compound is 270 grams per mole. The empirical formula also has a mass of 30 grams per mole, 1 carbon, 2 hydrogens, and 1 oxygen. Now, what we know about the relationship between the empirical formula and the molecular formula is they have to be related by a whole number. The true formula, or the molecular formula of the compound, has to be a multiple of the empirical formula. For example, it could be C2H4O2, C12H24O12, as long as it has that 1 to 2 to 1 ratio. Well, if the true compound is a multiple of the empirical formula, then the molar mass has to be a multiple of the empirical formula's mass. So all we really need to do is divide 270 by 30, and we'll come up with a ratio. So in this particular case, the molar mass divided by the empirical formula's mass comes out to be 9, and that means our true compound must be 9 times greater than the empirical formula, so it's going to be C9H18O9.